Title: UniGAP, a universal and adaptive graph upsampling approach to mitigate oversmoothing in node classification tasks. Abstract: this paper introduces UniGAP, a novel and adaptive graph upsampling technique designed to mitigate oversmoothing in node classification tasks. UniGAP is a universal framework that encompasses most current graph upsampling methods as variants. It can be seamlessly integrated with existing GNNs to enhance performance and address the oversmoothing problem. Introduction: graph data is ubiquitous in real-world applications, and GNNs are powerful tools for handling graph-structured data. However, increasing the number of model layers can cause node features to converge exponentially towards the same vector, a phenomenon known as oversmoothing. This convergence diminishes the model's expressive power and adversely affects its performance. Related work: oversmoothing represents a prevalent research issue within the realm of graphs, garnering significant attention recently. To assess the extent of oversmoothing, a variety of quantitative metrics have been established, including mean average distance, MAD, Euclidean distance, Dirichlet energy, and others. Previous research has explored various strategies to mitigate the oversmoothing problem, including manipulating graph topology, refining model structure, and dynamic learning. UniGAP is a universal and adaptive graph upsampling method that offers a universal framework for graph upsampling, encompassing most current methods as variants. Unlike existing methods that employ heuristic upsampling strategies, UniGAP adaptively calculates the probability of inserting an intermediate node for each pair of adjacent nodes in the original graph, generating a new upsampled graph through a differentiable sampling technique. Subsequently, UniGAP iteratively refines these sampling probabilities based on evaluation metrics, e.g., accuracy or smoothness, of the upsampled graph in downstream tasks. This iterative process strives to yield an optimally upsampled graph suitable for downstream applications. The authors propose UniGAP as a plug-in component that can be seamlessly and adaptively integrated with existing GNNs to enhance performance and address oversmoothing. Moreover, they demonstrate the potential of integrating LLMs with UniGAP to further improve downstream performance. Through extensive experiments, UniGAP shows significant improvements over heuristic data augmentation methods and integrates seamlessly with GNNs to enhance performance and mitigate oversmoothing. Components of UniGAP. The paper introduces UniGAP, a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. UniGAP consists of four main components: trajectory precomputation, multiview condensation, MVC, encoder, adaptive upsampler, and the downstream model. Initially, trajectories encompassing multiview information of each node are computed using the trajectory precomputation module. These trajectories are then processed by the MVC encoder to obtain condensed information, which is used to compute node insertion probabilities between each pair. A differentiable upsampling operation is employed to obtain the augmented graph, which is input into the downstream model for specific tasks. The paper provides an overview of UniGAP, detailing each component in depth. It discusses three strategies for trajectory computation: zero initialization, nonparametric message passing, and pre-trained GNN. For the multiview condensation, two strategies are introduced: trajectory MLP mixer, TMM, and trajectory transformer. The adaptive graph upsampler computes upsampling probabilities for each existing edge to decelerate message passing and mitigate oversmoothing. The augmented graph is generated using a differentiable sampling method. The paper concludes by outlining the pipeline of UniGAP and its potential applications in mitigating oversmoothing in graph neural networks. The UniGAP framework is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. It achieves this by learning the optimal structural representation for downstream tasks through optimizing the upsampling probability and the downstream model's parameters in an end-to-end manner. UniGAP's adaptive graph UP sampler module computes the upsampling probability for each edge, and the trajectory precomputation module initializes the node features for the new nodes. The framework also incorporates oversmoothing metrics, such as mean average distance, MAD, and Dirichlet energy, as regularization terms to ensure that UniGAP explicitly focuses on mitigating the oversmoothing issue. UniGAP can be integrated with various GNN models, and its effectiveness is demonstrated through experiments on both homophilic and heterophilic datasets. The results show that UniGAP significantly enhances traditional GNN models, especially on heterophilic datasets, and outperforms other graph upsampling methods, such as half-hop. The framework's ability to adaptively change the node's receptive field and learn the message passing dynamics enables it to mitigate the oversmoothing problem. Theoretical explanations for UniGAP's effectiveness are provided through closed-form solutions and lemmas, which demonstrate that UniGAP can learn the optimal structural representation for downstream tasks by optimizing the upsampling probability and the downstream model's parameters. The framework's complexity analysis shows that its time and space complexity are comparable to traditional GNN methods, maintaining efficiency. The experimental setup involves evaluating UniGAP on 8-node classification benchmark datasets, comprising 4 homophilic and 4 heterophilic datasets. The results are compared with various baselines, including traditional GNN methods, advanced GNN methods, graph transformer methods, and other graph upsampling methods. The evaluation protocols involve using public split settings, reporting the mean accuracy along with the standard deviation across 20 different random seeds, and integrating UniGAP as a plug-in method with various SOTA GNN models. Overall, UniGAP is a universal and adaptive graph upsampling approach that can effectively mitigate oversmoothing in node classification tasks and enhance the performance of various GNN models. Its ability to learn the optimal structural representation for downstream tasks and adaptively change the node's receptive field makes it a valuable tool for graph neural network research. The paper introduces UniGAP, a novel graph upsampling approach designed to mitigate the oversmoothing problem in node classification tasks. UniGAP is a universal and adaptive method that enhances the adaptability, performance, and interpretability of graph neural networks, GNNs. It is also integrated with large language models, LLMs, demonstrating the potential of combining LLMs with UniGAP. The authors evaluate UniGAP using various graph upsampling techniques and compare its performance with other state-of-the-art methods. They find that UniGAP consistently outperforms existing techniques in terms of node classification accuracy and adaptability. Additionally, integrating UniGAP with LLMs further improves its performance, highlighting the benefits of combining these two approaches. The paper also discusses the limitations and assumptions of UniGAP, as well as potential avenues for future work. For instance, the authors suggest that more intricate combinations of UniGAP with LLMs could lead to even more significant improvements in graph upsampling tasks. In terms of experimental details, the authors employ 8-node classification benchmark datasets, among which 4 are homophilic and 4 are heterophilic. They provide a theoretical analysis of UniGAP, which relies heavily on the work of 22. The authors show that when equipped with UniGAP, the model can learn the optimal node receptive field and message propagation process, making the model operate on the optimal graph structure. They derive each component of the optimization objective and provide a detailed proof of proposition 3.1. The authors also provide a proof of lemma 3.3, which adopts the latent space random graph model. They assume that the observed node features are projections of some underlying latent features with a Gaussian distribution. The regression risk with k-step smoothing is derived, and the rate of smoothing of the original MP is shown to be 2k. Finally, the authors compute the regression risk with k-step smoothing with UniGAP and define the upsampling probability at the optimal graph structure. They derive the expected value of the node features after one round of message passing and show that UniGAP can learn the optimal graph structure. Here is a combined summary of the 2 pages. The UniGAP algorithm is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. It consists of 4 main functions: trajectory precomputation, MVC encoder, adaptive upsampler, and downstream model. The trajectory precomputation function computes initial node trajectories, which are then condensed into multiview representations using the MVC encoder function. The adaptive upsampler function generates upsampling probabilities based on the condensed representations, and the downstream model function utilizes the upscaled graph to compute the loss and optimize the model parameters. The main function orchestrates the entire process, iterating over the epochs and invoking each function in sequence. The optimized model is returned as the output. Mathematically, the UniGAP algorithm is derived from the message passing process on the graph, assuming features of inserted nodes are the same as the source node. The recurrence relation is established by repeating the message passing process, associating equations to derive the connection between nodes I and j, and obtaining the expression for x(2k plus 1). The UniGAP algorithm is equivalent to a pseudocode identity, as presented in algorithm 1, taking the input graph G, MVC encoder parameters omega, UniGAP module parameters phi, downstream model parameters psi, and the number of epochs num_epochs as inputs. The optimized model is returned as the output. By adaptively upsampling nodes in the graph, UniGAP mitigates oversmoothing and improves node classification performance.